Hello all. In this lecture, we will look into the details of vibrational Raman spectroscopy. In vibrational Raman spectroscopy, we are considering the two important aspects. First one is Raman activity of vibration and the other is role of mutual exclusion. If a molecule has no center of symmetry, it is easy to decide whether the vibrational modes will be Raman active or not. In this case, we can assume these modes are Raman active according to the polarizability principle. Mu induced dipole moment is proportional is equal to the strength of electric field into polarizability factor. So, the radiation can sense polarizability in various directions of the molecule. For example, in the case of water, the polarizability is found to be different along all the three of the major axes of the molecule for the three different vibrational modes. But for spherical top molecules like CCl4, methane, etc., the polarizability surfaces are spherical, since they are completely isotopic as far as the incident radiation is concerned. That is, when a molecule possesses a definite symmetry, it is not easy to make a decision as much consideration is needed to understand whether the polarizability changes during vibration. Therefore, a rule is established, which is the rule of mutual exclusion, which states that if a molecule has a center of symmetry, then the Raman active vibrations are IR inactive and vice versa means the IR active vibrations will be Raman inactive. For a molecule not having center of symmetry, all the modes may be Raman as well as IR active. For example, if we are taking carbon dioxide which having a center of symmetry, its first symmetric stretching mode of vibration, we know it's IR inactive since it does not possess a permanent dipole moment. It is Raman active, and the other two asymmetric stretching and the bending vibrations, these three are IR active, so it will be Raman inactive. This rule may help in predicting the structure sometimes that we are considering the molecule N2O. If we do not know the structure, we can assume two structures, NNO and NON. For this structure, from experiment it is found that all the vibrations are both IR and Raman active. So, this result tells us that the structure 1 is the correct structure, as 2 having a center of symmetry cannot have both IR and Raman active vibrations. Next, we are discussing the vibrational Raman spectrum. For every vibrational motion, we can have the energy expression, that is EV equal to V plus half into nu bar E minus V plus half the whole square into nu bar E into chi E, that we are already discussed. The vibrational spectroscopy, the vibrational energy of vibrational levels is this, where the nu bar E, the equilibrium vibrational frequency, and the chi E is the harmonicity constant. The selection rule for Raman is the same as that of IR transition, that is delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. And the probability of transition to the second, third levels like IR decreases rapidly in the case of Raman transition also. Thus, for the transition from V equal to 0 to V equal to 1, the transition fundamental frequency of transition. First level transition, we are always having a fundamental band, fundamental frequency absorption, which is, you know, mu bar E into 1 minus 2 chi E centimeter inverse, the fundamental band. For V equal to 0 to V equal to 2 transition, and upwards we will get overtone, and for this transition the first overtone will be 2 mu bar E into 1 minus 3 chi E. We will get second overtone, third overtones, etc. in this transition, by the transitions in the vibrational level. As the Raman scattering is weak for overtones, we will focus on this fundamental transition only. That is, we are considering only the transition from V equal to 0 to V equal to 1 energy level. Hence, the Raman lines would appear at distances from the exciting line corresponding to each fundamental vibration. Therefore, the Raman lines will appear, for the fundamental lines, the Raman lines will appear by this equation, which is mu bar excitation plus or minus delta E fundamental centimeter inverse, where mu bar excitation is the Wave number of the exciting radiation, plus sign refers to anti-Stokes lines, and the minus line sign refers to Stokes lines, as we were dealt in the rotational Raman spectrum itself. That is, the minus sign or Stokes lines indicate that the molecule takes up some energy from the incident radiation for the vibrational transition, so that the energy of the scattered line, that is the fundamental Raman line, will be decreased than the excitation line, where we are applying the minus sign, and the plus sign refers to anti-Stokes lines, which means that the molecule is already in the upper level of vibrational state, so that it gives, or it may give the energy to the molecule, for radiation, and the frequency of the radiation will be increased from the exciting radiation. As the rotational levels are much more closely spaced than vibrational levels, rotational Raman spectrum contains even more intense lines. But in the case of vibrational levels, they are some more spaced, and so the anti-Stokes lines are very much less intense. And it is very difficult to observe molecule in the, as it is very difficult to observe the molecule in the first vibrational state, transition intensity will be very less than in the case of rotational Raman spectra. That is, for vibrational Raman spectra, anti-Stokes lines are very difficult, or maybe in low intensity, appearing in a very low intensity. Next is, we are considering a vibrational Raman spectrum. It's a very simple to interpret, that it shows a series of intense lines. You can see it is the series of intense lines in the less frequency side of the exciting radiation. So the intense lines you can see in the less frequency or wave number side, with a much weaker mirror image series on the high frequency side, corresponds to anti-Stokes line. The separation of each line from the center of the exciting line provides the Raman active fundamental vibrational frequency of the molecule. By this, I am concluding the discussion of vibrational Raman spectrum. Thank you, dear.